So finally, let us consider a more realistic scenario in which anything that can possibly go wrong will eventually go wrong. So we are talking now about quantum computation with faulty components. Your state preparations, your measurements, your quantum logic gate, just about anything can go wrong, can be faulty. Now, is there anything we can do in this kind of scenario? Is there any hope to protect our quantum computation? Yeah, well, there is some hope. You know, there is a flickering light at the end of this quantum tunnel. We are still in the quantum tunnel, to be sure. It's terribly difficult to implement things I'm going to tell you about, but there is some hope. So the idea is to use good quantum error correcting code and fault-tolerant design, such as transversal implementation of quantum logic gates, and frequent error recovery as you compute. So you interspace your quantum operations with error recovery units, and you hope to recover from errors faster than you generate errors. So that's essentially the idea. Now, so let me just give you a simple example how it works, because there's another component here which is about concatenating codes, to which I'll come in a moment. So let me start with our simplistic quantum circuit, and I want to implement this circuit in a fault-tolerant way. So what do? I just have 2 qubits here, 2 quantum logic gates. As it happens, it's kind of an easy case because those 2 logic gates are both Clifford gates, but just to give you an idea how things work. So we take each qubit here and encode it into a block of 7 qubits. I'm just picking up the 7-qubit code because it is good for pedagogical purposes, because I know that the Hadamard and the control node can be then implemented in a transversal way. So after encoding each qubit into a block of 7 qubits, I then implement the Hadamard and the control node in the transversal way. As it happens for this particular code, the logical Hadamard and the logical control node can be implemented in a transversal way, which is very nice and convenient. But after each implementation, I will add error recovery units. So I interspace my implementations of quantum logic gate with those yellow rectangles here, which represent error recovery. So there are some quantum logic gates. They all, for this kind of code, they all involve only the Clifford gates and the syndrome measurements and the recovery and so on and so forth. So if I have, at most 1 error, those error recovery units will nicely clean the error. If there's only 1 error per block, then the frequent error recovery unit will clean the circuit for me. Now the transversal implementations make sure that the error will not multiply badly, right? So if I have, say, bit flip error somewhere here, then okay, the control node will just generate another error in this block, but it will just only generate 1 error in this block. So it's not that bad. If there are no other errors here, then this error correcting unit here will just pick it up and clean it. Now, of course, we can also assume, and that's very important, that errors can appear in our error correcting units. It's in fact, in this case, if you look at this logical Hadamard followed by this error correcting units, so it's more likely that error will actually appear within this error correcting unit. But then the hope is, if it is this at the most 1 error, it will be just picked up by this error correcting unit, so the subsequent one will just clean it up. So, of course, the assumption here is that the errors are small. And so how can we make sure that the errors are really, that the probability of error is very low? Well, we can reduce probability of error by concatenating codes. So remember that we did it actually once when we look at the Shor code, 9-qubit code. We took a 3-qubit repetition code that was correcting for bit flip errors, and then we encoded every single bit in that code in 3 other qubits. That was to protect against phase flip errors. So we are going now to play with a very similar idea here. What we are going to do is not to encode our original qubit once, but k times. So we start with say level 0, where we have our raw qubits, our physical qubits, and then we do the first encoding. So we encode every single qubit here into 7 qubits, and then we do it again. So we go from level 1, and hopefully at level 1 we reduce the probability of error. So this code will correct for 1 error, so will only fail when you have 2 or more errors. And so you have 2 or more errors, assuming that errors are independent. It's actually, it can be a weaker assumption, but say, assuming that the errors are independent, then the probability of failure is proportional to p squared. Now this number here, the magic number c in front of p squared, is actually quite important. It represents the possible locations for errors. So it just tells you, okay, 2 errors can happen here and here and here and here and there. So it depends a little bit on the code, a little bit on the way you implement your fault-tolerant design. But it is a fixed factor, right? So for a given code and a given sort of way of implementing quantum logic gate, C is fixed. Now the inverse of C will play an important role. It will just be called, we call it P threshold, the threshold probability. Now we just want to make sure that we gain when we just go from P to C times P squared, and that can only happen when P is smaller than 1 over C, right? So we are below threshold, in which case we really gain. So this number is smaller than this one. And you know, we can do this encoding again and again and again. So when you iterate this and you go to sort of a k level of encoding, the error, the effective error, the error of your logical operation, in this case, for example, logical Hadamard or logical C-node, goes very, very rapidly to 0. So you see it goes doubly exponentially with k to 0. So this is actually a fantastic way to reduce error on this logical unit. You just do encoding, you concatenate your encoding k times. So this now is effective error, right? So now this is the error per this component, per this rectangle on the diagram, in the diagram here in the circuit. So that's good, but of course, you know, you may worry at this point that the price to pay is that we have to just replace at every single layer. We just have to just replace our Hadamard with another fault-tolerant implementation of Hadamard, and the error-correcting units, every single gate in the error-correcting unit is then replaced by a fault-tolerant implementation of this error-correcting unit, and so on and so forth. So what is the price to pay? Are we gaining or are we not gaining these things? Are we perhaps putting lots of extra gate into the whole thing to accommodate this rapid decrease in the error? So suppose you have a generic quantum circuit with n, capital N gates, and suppose that at each layer of encoding, if you go sort of 1 level down, you need at most R gates to implement in a fault-tolerant way every single gate at the higher level. So if you do the concatenation, so the number of gates required will go from n to n times r at the level 1, and you do it again, so it's going to be nr squared, and at the level k is going to be nr to the k. So now suppose that we want to have this circuit operating with a certain probability of failure, say epsilon. So we want this ideal circuit to give us a correct answer with probability 1 minus epsilon, and the probability of error is epsilon. So that means that the probability of error per component is epsilon over n, because we just assume that if one component goes wrong, then the answer may be wrong. It's not always the case, but you take the worst case scenario. So this effective error that I here express in terms of the threshold probability, which is the error per unit per component, should be smaller than epsilon over the number of gates. So now you can fix your preferred epsilon. It could be something like 1/3 or so. Anything below 2 is fine. Then you can just, once you have your epsilon and once you have your n, and you know your probability of thresholds, and so you can then estimate the value of k, so how many levels of encoding are needed in order to satisfy this condition. And so you can do a simple calculations. You can just, your task is actually to evaluate what is 2 to the k. So if you, what I did, I just said, okay, this term here on the left hand side is equal to this roughly. So I took log on both sides, and rather straightforward calculations gives you the expressions for 2 to the k, and then you can, from that you can get expression to r to the k, right? And then you can see that actually the price to pay is not that huge. The final expression that you have for number of gates that are needed for number of operations in this particular case, so the size of the circuit is the original size, that is n, multiplied by expression that is polylogarithmic in n over epsilon. So that's very reasonable scaling. And that result is known as a threshold theorem. It basically tells you that quantum computation of any length with circuit of any size n is possible with faulty components as long as your faulty components operate below, with probability of error below a certain value, p threshold, which is determined by the codes and the way you implement fault tolerance. So as long as you reach this level of precision, you can implement any quantum computation in such a way that the computation will go wrong with probability epsilon. And the price to pay, this concatenation coding and so on and so forth, is such that the size of the circuit will grow. So you have to replace this circuit with many more quantum gates. The constructions will be much more complex, but the increase goes like polylog n over epsilon, so it's not too bad. So that's a good result. So that's our hope. That's what we hope for. Now I should perhaps say that of course there are many simplifications here. The major issue, of course, is that in this example, I pick up a code that allows for transversal implementations of all gates from the Clifford group. And the Clifford gates for any error-correcting codes which are based on stabilizers are kind of easy. The real challenge is to include those non-Clifford gates, like the T gate, and implement them in such a way that it's fault tolerant. So that's a real challenge, and there are a few ideas how to do. People do some magic states, some teleportation tricks, and so on and so forth. I let you look it up. I'm not going to discuss this, but just to let you know that the difficult part is actually maybe not what I described here. I just wanted you to see the good side of quantum, or easy side of quantum error correcting codes. The more challenging side, implementing T-gates is something that it's probably fair to say is still waiting for good solutions. And it's if we choose some other codes, we can implement T-gates in a clever way, but then we may have a problem with some other gates. So we can implement T in a transversal way, but say Hadamard gate is more difficult to implement. We may also look for other ways of stabilized quantum computations. There are some topological methods, there are some other things you can consider. So stabilizer code is not the only way to go, and so the whole field is an active area of research, I have to say. Probably the most interesting and the most important part of quantum computation, because it really matters at this point whether we can implement those devices or not. And this fault-tolerant result tells you, yeah, there is a hope. There's a long way to go, but there is a hope. So as a postscriptum, I forgot to tell you what are the values of this P threshold. This is actually our critical magic number. If you talk to experimentalists, this is the number he or she will be really interested in, right? So that's the P threshold. What is the precision of your component that you are aiming at? Because you know that once you're below this number, then miracles are possible, right? We have this brave new quantum world waiting for us. We can scale our computation. We have this threshold theorem here. Well, now of course this number depends on quantum error correcting codes you use, what kind of fault-tolerant design you use, and so on and so forth. But no, obviously the question is, what is the best we can hope for? Well, those numbers are somewhere in the order of 10 to minus 4 to 10 to perhaps minus 2. There is, of course, a difference between some theoretical modeling, and if you do some numerical calculations and have a specific implementations for some specific purposes in mind, that could be much better. It could even be a few percent or so. But this is a roughly sort of the order of magnitude we are talking about. So we do hope that we will have those components, and we will be able to implement quantum error correcting codes in a fault-tolerant way and scale up the whole thing.